One of our stars of the show.
Hello, everyone. Yeah, my name is Ansgar. I'm at the Ethereum Foundation, and I was basically just wanting to take some time, explain a little bit how we think about blockchain scalability, especially kind of my perspective on things, and then how EIP-4844, which I think has had a little bit of publicity over the last few months, how that basically fits into the picture and why we're doing this in the first place. And so the idea is I want to basically first kind of give a general motivation of why exactly do we have this roll-up-centric roadmap, right? How does that fit into our scaling vision? Then specifically talk about the data availability side of things with what you might have heard, the kind of the term dunk sharding, how this fits into the plan, and then round it up with like a long-term vision of kind of the chain architecture we are going towards there. So let me start. Why rollups, right? Why do we basically need them in the first place? And I want to kind of start a little bit abstractly by talking about what I like to call like execution chains, but it's basically just user-facing blockchains, application-facing blockchains, right? And so the very first one we had was Bitcoin, of course. It's a special purpose, the very first blockchain ever. Then Ethereum came on the scene, first general purpose execution chain, and basically with all of these chains, I mean, of course, there have been thousands since. The goal is always to have maximum functionality and maximum throughput, but at the same time, and this is kind of where the fundamental tension with blockchain comes from, you always need to ensure security, right? And so I think one way to illustrate this really well is with this graph. It's of course a little bit of a silly toy graph, but just to get you the intuition. So basically, the fundamental trade-off here between the cost to run a full node for the network versus the throughput you can achieve, right? And so you can put Bitcoin and Ethereum roughly in these positions in the graph. So Bitcoin, very, very limited minimal requirements to run a node, but also very limited throughput. Ethereum was willing to trade this off a little bit more, but the goal was always, even with Ethereum, that you have to be able to run your full node at home without too much effort, like on Raspberry Pi, right? Everyone can run it locally. And the problem, though, is that means that basically everyone in the entire network validates everyone else's transactions, right? And that just fundamentally, of course, cannot scale. If we have billions of humans on Earth, you can't validate everyone's transaction on the other side of the world if they want to buy a coffee, right? So naive kind of iterations on this, of course, what you could do is like, what if we just keep going up this diagonal, right? And then this is kind of more with like a, don't take this too seriously. I just put this like a logo just for example purposes, right? But there are chains that basically just are willing to say, okay, what if we just keep increasing the requirements for running a full node, right? And I mean, it's in a way perfectly legitimate, right? It's just another place in this trade-off space. The problem here is, if I don't run my own full node at home, and there's ever a disagreement about the state of the chain, right? I basically only have two choices. I can either just, look what the majority of nodes claim, and I just go with it. That means that if ever the majority votes to, steal all my coins, I would go with that because, again, I just follow the majority. So all of a sudden, I basically lose the trust guarantees that I get with locally verifiable chains. Or, of course, the alternative would be, if there's ever disagreement, I just stop and I go on Twitter and I see, basically who claims what was the problem, and I just wait until basically there's manual social resolution. So now, basically, where on this graph, what is the problem here? Like, where would we want to end up on? And of course, this place, this ideal mythical unicorn place that we want to end up in is kind of this upper left corner here, where the cost to run a full node for this kind of network is still very low, but at the same time, we somehow get super high throughput. And in practice, actually, like the way Ethereum and the rollup space goes, this doesn't have to actually be one rollup. This could, kind of one step ahead here. One blockchain, this could also be like just multiple kind of parallel ones with lower throughput each or something. It doesn't really matter. The thing is, how do you basically, with only running a small full node, get a total throughput like that is very high, right? So how can we do this? And the intuition, in a way, is, if we just go back briefly here to this other one, right? The problem here was, if there ever is a disagreement and I don't want to trust the majority, I basically have to always stop and then manually socially recover on Twitter. Someone explains to me what was the problem, how, who was right, and these kind of things. So the idea is just, what if we, automate this step? What if we find a way with like a chain that I can't necessarily directly locally verify, what if computationally there was a way for me to basically check integrity, right? To either, if there was a problem, you know, to have a trustless way to resolve this computationally, or maybe even, you know, do one step better and check the integrity from the first place. And this is kind of exactly where we get to rollups. So the idea for rollup is you have a chain that, in this case, of course, I kind of want to explain both optimistic and ZK rollups. So you have a chain, but you just, you know, you don't have to run a full node for that necessarily. You can just apply all the changes optimistically that you know, you just like, someone tells you, you know, this latest block made these changes, you just trust them. But then, this is the important thing with optimistic rollups, anyone, whenever there's a disagreement, right, as long as one person notices something went wrong, they can submit what's called a fraud proof. And instead of having to go on Twitter and having someone explain this to you, your computer just automatically resolves the challenge for you, right? So as long as you always wait for the settlement period, even if you don't actually run the chain yourself, you always can trust that whatever you see on the, like, as the latest finalized chain state is actually valid and computationally with computational integrity, right? So this is an amazing trick for basically trusting chains you don't verify yourself. And the only thing that needs is, of course, it needs a settlement platform where you can actually run this proof, right? And so then the same thing with ZK rollups. Basically, the only small change there is that it's, you know, using fancy cryptography, so you don't even have to wait for a challenge and run a fraud proof. It immediately comes with what's called a validity proof. So it checks, it ensures the computational integrity right when you make the kind of the state transition in the first place. But basically, same idea. You don't have to run the system to trust it. That's basically the magic here of rollups, as long as you have a settlement chain that you can rely on. There's one small asterisk, and this is kind of what the kind of the motivation for this talk came from, and that's why we have to talk about Danksharding in a second. There's one really important asterisk here, and that is data availability. And data availability is, unfortunately, like a topic that's not obvious to understand. And so basically, I gave two examples here on both sides, what like the problem here is, and I want to just take a second to make sure, like, if you take one thing out of this talk, then ideally it would be to really understand why data availability is so crucially important. So with any rollup, right? If you do not, you basically, if you have a system, a layer 2, something like Optimism or so, and it commits onto the base chain, right? The idea is anytime there would be fraud, you can detect it and then submit a fraud proof. There's one assumption here. The assumption is that anytime they make an update, they actually tell you what the update was, right? And this is crucially important. If they don't do this, right? If they just say, oh, I made an update and now you don't have any balance anymore, and you know you didn't actually send a transaction, right? There's no way for you to prove a fraud if they don't actually tell you what supposedly happened, right? So basically, if they only give you the update without explaining what supposedly happened, there's no way for you to challenge this. And similarly, with a validity proof, it's not quite as bad with ZK rollups because, as we're saying, there's cryptography that always checks integrity, so they can never steal your funds. But if they don't tell you what actually happened, you have no way of knowing what the current chain state is, and so you only know it is a valid state, but you don't know what the state is, and so you cannot no longer use the rollup. So they can lock you out of the rollup. So if they don't actually, and what I mean by basically telling you what actually happened, it's just basically giving you what you know from Ethereum, like a list of transactions, right? Every block update that they do, they basically have to actually tell you the list of transactions they supposedly run. Otherwise, this entire system doesn't work. So basically, making sure that the transaction data was actually published. This is at the very core of data availability and what we need to make this entire system work. And so not only do we need settlement, the settlement layer, which, I don't know, I tried to put emojis on everything here, but we also need this kind of data availability layer. And our approach for scaling this, of course, is Danksharding. And so now I basically want to transition that into talking a little bit about Danksharding. So what exactly, how exactly is data availability scalable? So the first thing there is, I think it's really important to understand the difference between the different types of data, right? Today, on Ethereum, we only provide one type of data, and we call this call data. I'm not sure, like most of you, I'm not sure how technical you are, but if you've ever sent a transaction on Ethereum, basically, if you look into the details at MetaMask or something, if you send a Uniswap trade or so, it always sends a little bit of data with the transaction that actually tells Uniswap what it is supposed to do, right? Like which token you're supposed to swap with which other token, and that is what we call call data, right? Because it's just context for the call you want to do. And for this type of data that we process on the base chain, there's two really important properties here. The first one is that during the execution of the chain, if I'm running an Ethereum node, I actually need the entire data locally because, again, I have to, if I want to run the transaction, I have to actually know what Uniswap is supposed to do. So I need this data locally. And then also after I execute it, I actually store it in my history file. Like for now, Ethereum, if you run a node, you literally store all the history from the beginning of the chain. In the future, there's an EIP called 4444. Don't confuse it with 4844. Unfortunate naming collision there. But basically, in the future, you'll only keep like the last year or so of history, but it's still quite a bit of commitment of keeping this data around for a long time. Now, rollup data, for now, basically, what rollups do, if you actually ever want to look at at Optimism, like zk-Sync, one of these rollup systems, and you actually go on-chain, on Etherscan or something, and you look what actually happens whenever they publish a block, you will see that they literally just take a lot of this data that they want to, improve availability of, and they just all put it into like a huge chunk of call data. But it turns out we can do better. And so why can we do better? Because rollup data actually is fundamentally different in nature here. As we were saying, we only need to guarantee data availability. Like this is the crucial point here. We already talked about this. But the transactions don't actually need the data, right? As I was saying, like Uniswap actually needs the data because it needs to know what you're supposed to do. But the rollup never actually processes the data on the layer one, right? Like the layer one is only, a very dumb, simple settlement layer. So it only actually needs a pointer. It only needs to know data with this hash or with this, commitment was made available. It doesn't actually process the data. So it is like a different type of availability it needs. And also, once we have ensured that everyone had access to the data, the layer one can forget about it. It's not something you have to actually store in your history, right? You just know if everyone, agreed back in the day that it was available, you don't care anymore, you don't have to store it. So this is two very different types of data. And so the idea here is we want to give it its separate form, and we want to then use that form to really scale the throughput for only the right side of data. The left side of data will not ever fundamentally scale on Ethereum. The right side will. This is basically the crucial insight here. And just to kind of hammer this point home a little bit, basically, what actually is data availability? Again, there's a lot of confusion around this. It is only the assurance that the data was not withheld at the time the availability guarantees were made, and that basically that the data was indeed successfully and widely published. And importantly, this means that it is not some sort of long-term storage. It is not some sort of forever continued availability, right? It is a one-time, you can think of it as a message board. You put a note on there. At that moment in time, the data was available. So then, how are we going about actually, giving it its own type of data and starting to scale this? And this is basically a two-phase approach. And the first of these two is the EIP-4844 that I was mentioning, that you probably have heard about, also known as proto-danksharding. We like having fun with naming, so I guess this happened. And fundamentally, what does the EIP do? It's actually not that complicated, and I apologize for not having pictures for this, but I'm more text kind of person. So what it does is basically, it introduces a new type of data, right? And we call this data blobs. Just because fundamentally from the layer one perspective, it's just like a huge chunk of data. We don't care what's in it. We don't actually ever look inside, right? So it's just a blob of data, and we collect multiple of those just per each block that we produce on Ethereum, right? And so right now the choices, although these parameters can still change, the EIP is not yet live. So right now parameters are 128 kilobytes per blob. And basically, every block that Ethereum produces will come with a separate section, right? So there's the main block, and then there will be a separate section that just basically is only like a list of raw blobs. And for now, we're kind of thinking up to 4 blobs per block, so it's like up to half a megabyte per block. But again, you know, these numbers can change. And then we also introduce a new way of actually using this data. We call it a blob transaction. It's very simple. The only important thing you have to kind of understand is, and it's called commitment hashes, but basically the transaction doesn't actually include any data of its own. It only includes like a pointer, right? It only says, basically only put this transaction on chain if you at the same time also, you know, have a blob that has this hash or something. And then when you send the transaction through the network, you just send the blob separately. And then basically the person that actually creates the block just takes the blob, puts it into this little blob section, and puts the main transaction into the main transaction section, right? So this is basically, it's starting to really separate the data out from the main transaction. And importantly, this is like a point that's often overlooked, and that's actually where my involvement with this EIP was. We want to start making kind of this useful for rollups as soon as possible, and as you see, we will bring this EIP to the chain later this year. And what is the most important thing for users? Of course, price, you know, how expensive versus cheap is it to use my rollup? And so what we are going to do is, as a first step in making this data more useful, is we will basically give it its own pricing market, right? So this means right now, when you use a rollup and on the main Ethereum chain, there's some sort of NFT drop or a USDC DPAC or, you know, all these fun things that happen from time to time. Basically, rollups have to compete with all this normal layer 1 activity. In the future, they will no longer have to do that, right? They have their own little section, the blob section, and we will have our own EIP-4844 style mechanism that just, you know, keeps track of how much demand there is for these blobs, and it gives these rollups their own blob price. And so on the main chain, there could be an inferno of activity, and you can still, you know, publish your rollup data just fine. So this will fundamentally make data much cheaper for rollups as a first step, and make rollups for users more useful. And again, later this year already. And then, why is this basically just the first step? What do we have to do to get to full dung sharding? And I mean, this is of course, like, this is a million miles kind of summary, right? This is not, I was tempted to go into more detail here, but kind of, I think basically this is really kind of the TLDR that you need to understand. So with the EIP-4844, we still, you know, we split out these blobs, but they still come with every block, right? If you run a node, you still download the entire blob section. And of course, this still limits scalability, right? If I still have to download everything, there can be maybe 4 blobs, there might be 8 blobs, 16 blobs, but there can never be like 100 blobs, right? It's just too much data for me to download. And so this is kind of where the fundamental scalability of the system will come in. And this is by taking the section, we will erasure code it, right? If you're like technical, basically non-technical, this means we give it some extra information just to make it more redundant. And then nodes will start to only sample the section. This is really important. Again, if you don't understand that, it's fine. But the idea is basically that in the future, you still download the main block of Ethereum, but you only sample the blob section. And this means that the blob section now can grow in size much quicker, much faster, to a much higher degree, because nodes fundamentally, basically, we are no longer, you know, when I don't want to go back to the very beginning of the presentation, but we were talking about the limits of what an individual node can verify. And because the individual node no longer has to download the entire thing, we can basically now start really scaling the throughput of the system. The problem here is just that, you know, as with any research topic, it's tricky to get right, and so there are quite a few open networking topology questions, like how do you exactly set up the sampling, who is responsible for which part, you know, how does everyone come to agreement on what was available, what was not. So it's still a research project, it's already pretty advanced. I mean, dung sharding, the term, has been around for over years, so I think we are pretty far along in this way. But what we expect is that we will basically roll this out over time, in the next few years, like maybe an initial version with still limited throughput, and then as the network gets more robust, keep increasing this throughput. So basically, but this is the road, right? Left is the EIP-4844 is a one-time gain, and then the right is a roadmap that will get us step by step as the demand for rollup grows. This will get us to, you know, the full super high scalability that we all deserve on Ethereum. And this, again, this kind of like was more me trying to like have a little kind of explainer for why data availability is so important and what we're planning to do about it. Now I want to kind of take some time towards the end and give a little bit of an intuition of like more abstractly again, like what does this mean for the Ethereum chain, and how does this the kind of I'm sure you've heard the term the modular vision. Basically, where are we headed here? Again, I want to start like this, just the picture that we already know from the beginning, just like it's a simple execution chain, Ethereum, Bitcoin, whatever, right? It comes with its own security. That's what the little box and with the and settle on top, right? And so this is exactly what they're going to do. So now in this picture, we have something that all of a sudden now we call a rollup, but in a way, the rollup is also just a blockchain, right? But the rollup now, in this picture, it's an enshrined rollup because there's only one rollup for one settlement chain, right? You could also call it the other way around. You could say it's an enshrined settlement chain. End up in what people used to call the multi-chain vision. I think these days it's a little less popular, and I would say for good reasons. But basically, this is in principle a perfectly viable picture. So every chain does its own little enshrined rollup trick to gain scalability. Everyone does their own settlement, their own data availability scaling, and you end up in this picture. And the important point here, though, is that as you can see, everyone has to provide their own security. So all these locks are pretty small. You know, everyone has relatively small security because it's fractured across the system. And you know, the dotted lines, the bridges between independent chains are very brittle because you never have shared security. So you basically always get for any interaction of two chains, you always get the worst security of the two. And if you have like interaction between 20 chains, you get like the worst security of all 20, basically. And of course, again, duplicated complexity. You have to basically re-implement these scaling solutions for every blockchain. So what is the alternative? The alternative here is what we call a shared settlement chain. So the idea is that instead of having every chain/rollup live on their own settlement layer, we just put them on top of the same settlement layer. And what this gives us is two things. One is we have now shared security all of a sudden. Like, as long as the settlement layer here, settlement chain, is secure, all these rollups are secure. I mean, you know, barring smart contract bugs or something. And of course, this doesn't mean you get security for free. That's why I call it pooled security. Just to basically briefly mention, what we would expect is that, like in practice, we would of course see some sort of hybrid, right? We have several settlement chains with some maybe even still monolithic chains, and they all interact. But our thesis is that basically this will over time be the most popular model, and basically most activity will accrue on top of one base settlement chain. And then with that, kind of like, how does Ethereum fit into this? Just to kind of briefly walk through these pictures as well. So Ethereum started out as a pure execution chain with proof of work security before rollups were even a thing. And this is, you know, I always like to do a little bit of Ethereum history archaeology, right? And so this, if you see April 2019, this is pretty amazing. Like Casey Dietrichs was one of the researchers back in those days, and this is 3.5 years ago, and he was already basically talking about using ETH2 as a pure data availability engine. This was the first time someone basically conceptualized this and put this into these terms, right? Like, instead of doing these shards with execution environments, what if we just use it for data? And then, of course, a year and a half later, Vitalik had this pretty famous article about rollup-centric Ethereum roadmap. And just a little shout out, a former colleague of mine, he's now at the Geth team, Matt, who also talked about how basically our original ETH2 plans were like a roll-up system from the very beginning. So what did that mean? Basically, we started having roll-ups, so we basically started giving settlement and data availability functionality to Ethereum, but as you can see, the data availability symbol is very small, right? It's only very limited data availability, so we could put like a few roll-ups on top, but it's pretty expensive. Then we introduced the beacon chain, of course. As you can see now, all of a sudden with proof of stake, we get like really good security, but first we had to merge, so we merged. So now we get this amazing security of the proof of stake chain, but still very low data availability. So what are next steps? Next step, proto-dank sharding, EIP-4844. As you can see now, all of a sudden our data availability symbol is a bit bigger. You know, good, but only a first step. In order to really get to this amazing high throughput settlement layer, we need full dank sharding. And so once we have full dank sharding, we can basically go to this picture. That's where Ethereum, wants to end up. As you can see, there's like a little wrinkle because our settlement chain will not be a pure settlement chain. We will still have execution. If you really want to, you can still use Uniswap or whatever DeFi you want on the base chain itself. It will just be really expensive. But we will be able to have whatever high throughput system we want on top. This could be 1 billion rollups. This could be like a few really high scalable rollups. Basically, this gives us all the scalability we ever want and need. And with that, I hope that kind of gave a little bit of an intuition. I'm not sure if I have time for questions.
Do we have any questions? Anyone want to raise their hand?
Thanks for
we have 2 minutes.
Being here.
Anyone? All right. Let's go for it.
Thanks for the great talk, Ansgar. Talking specifically about 4844 and your observation, are there any unresolved problems with that EIP, or is it ready to be shipped?
Oh, this is a great question. So basically, are there unresolved questions? Is it ready to be shipped? And indeed, the good news is that it's all basically ready. There are some tiny details that are right now being worked out around how exactly are these is these blob section transmitted through the network. Initially, we wanted to literally just shove it, attach it directly to the block. Now we want to transmit it separately. So this is implemented right now, but there's no open research needed. Whereas with full dank sharding, there's still a bit of a way to go.
Got it. Thank you so much. That was awesome.
Yeah, absolutely. Great explanation, great visuals through the entire talk. Do we have any other questions? I could probably take one more.
Hi. So is part of this proto-dank sharding, like, can we have data availability of the Ethereum as well? Like, is that part of this work as well? Like, has that thought been put into this?
So the question is, can we have data availability off of Ethereum as well?
Yes. Like,
yeah. So actually, this is a really good point. And if I just briefly go back to this picture, basically, it of course, it assumes that we always, have settlement and data availability in one place. And actually, in my longer talk on this specific kind of way of thinking about things, I also had a picture where basically there are alternative approaches. You can take the data availability and you can separate it out. And for example, systems like Celestia are basically doing exactly this. They only focus on being a pure data availability layer. And so if you are a rollup on top of Ethereum and you want to use Celestia data, maybe you even want to use Bitcoin data, SegWit data for data availability, you can do that. There's one asterisk though, and that is that now basically your trust assumptions are that both the settlement chain, so Ethereum, and the data availability chain, Celestia or Bitcoin or whatever else, both of them have to be secure and hold in order for your system to be secure, right? So basically now you get the weaker, so basically you lose this shared security assumption a little bit. And now if you want to have multiple interoperable rollups, basically they have to either share the same data availability layer, or otherwise they basically get the minimum out of all the data availability layer security that they use. So basically there's like an asterisk around shared security. But other than that, in principle, it's possible.
All right. If you want to ask Ansgar any questions, you can catch him as he comes down from the stage. Let's hear it for him one more time, everybody. Amazing talk.